Welcome to Dynamic Relationality Theory for Modelers. This series explores the mathematical and conceptual foundations of dynamic relationality theory, or DRT, and its application to modeling complex systems. Today, we are starting with the basics: the interplay of the virtual and actual, the role of assemblages, and how gauge theory provides a framework for visualizing transformations. Let's begin with a fundamental question. How do we model this dynamic evolution of systems while capturing the interplay between potential and reality? At the heart of DRT are two intertwined dimensions: the virtual, representing latent possibilities and emergent potentialities, and the actual, the tangible outcomes, processes, and structures we observe. These dimensions are not independent. Instead, they co-evolve in a dynamic feedback loop. When potentialities are actualized, they transform into realized configurations. Simultaneously, the actual reshapes the virtual, generating new possibilities for innovation or transformation. For modelers, this duality highlights the need for tools that capture emergent properties and recursive feedback. This is where gauge theory and functorial transformations offer critical value. In formal terms, the virtual can be modeled as a topological space of possibilities, while the actual is a specific configuration within that space. This interplay ensures that transformations are both directional and iterative, offering a pathway to model systemic adaptability. Assemblages are dynamic configurations of entities such as teams, technologies, or processes that co-evolve within ecosystems. In DRT, each assemblage has two key aspects. First, content: the tangible elements, resources, systems, or operations. Second, expression: the relationships, meanings, and signals generated by those elements. This duality is captured through double articulation. First articulation maps the material organization of the assemblage. Second articulation captures the symbolic and relational dynamics, enabling meaning-making and adaptability. Mathematically, assemblages are represented as categories. Objects symbolize entities within the system, and morphisms represent transformations or relationships between those entities. For example, in a healthcare ecosystem, patients, data systems, and providers form objects, while morphisms model processes like diagnosis or information exchange. This structure allows us to analyze both localized interactions and their broader systemic implications. Assemblages also operate within topological spaces, with each point representing a distinct state or configuration. Using smooth manifolds, we can model the continuous transformations within an assemblage and reveal the vector fields driving these changes. Let's dive deeper into how we model transformations across relational dynamics using gauge theory and functorial domains. First, gauge theory. Gauge theory provides a way to model transformations while preserving the system's internal consistency. Gauge fields capture how relationships shift locally, whether through internal evolution or external intervention. These shifts propagate across a system, maintaining coherence at a global level. Imagine a digital ecosystem where user behaviors, algorithms, and platform policies interact. A change in one area, such as an algorithmic adjustment, influences the entire network. Gauge theory maps these cascading effects, revealing both opportunities and risks for intervention. Second, we have functorial domains. To map transformations across assemblages, DRT uses functors. Functors connect different categories, ensuring that relationships and dynamics remain coherent as the system evolves. For example, a functor could map operational workflows in one department to strategic objectives across the organization. These mappings allow us to model how local changes, actual, reshape potentialities, virtual, and vice versa. By integrating natural transformations, we can also model the process of evolution itself, capturing not just the starting and ending states, but the pathway of change. One of DRT's strengths lies in its use of topological representations to model relational configurations. Smooth manifolds represent a system as a continuous space, where each point corresponds to a unique configuration of objects and morphisms. Open sets within these manifolds reveal localized practices or subsystems, while their overlaps highlight collaborative dynamics. Topological tools like vector fields and Lie derivatives help us quantify the direction and magnitude of transformations. For instance, a vector field might represent the flow of data between departments. A Lie derivative measures how these flows evolve over time in response to external forces, such as new technologies or market pressures. These tools allow us to model ecosystems as both adaptable and resilient, capable of responding to change without losing coherence. Here is what we have covered today. First, virtual and actual dimensions. Understand how potentialities virtual and realized states actual interact to drive systemic evolution. Second, assemblages and double articulation. Use categories to model relational dynamics, capturing both material and symbolic transformations. Third, gauge theory and functorial transformations. Visualize how local changes propagate through ecosystems and map relational dynamics across domains. And last but not least, topological tools. Represent systems as smooth manifolds to analyze transformations in a rigorous, continuous framework. With these foundations, DRT equips you to model not just the components of a system, but the dynamic relationships that shape its evolution. Thank you for joining me on this first episode of Dynamic Relationality Theory for Modelers. In the next episode, we will explore how transformations propagate across strata using advanced tools like sheaf morphisms and transversality. Until then, start thinking about how gauge theory and topology can refine your models of relational systems.